Hello everybody, thanks for joining my session on my presentation on a closed solar thermal receiver for air at ambient pressure. We will talk about the concept and the basic design with first manufacturing and testing. Solar power exceeds all other energies on this planet. So we look here, the small black sphere, that's the world energy demand per year. And the other gray spheres, these are the conventional resources that we have, and their size is what we have at all for forever. And now the yellow sphere, that's what we receive on solar power per year from the sun. So we don't need all these conventional sources, we just need to utilize solar energy and we're fine. Now we know for the daytime the matter is more or less resolved. We can do this with photovoltaic. We only need to set up enough panels and we are fine. However, anybody who is doing that realizes, oops, I need to get through the night. And batteries for utility scale applications, it's a questionable thing. So what we should do, we should unlock the potential to go through the night with solar power. And the features of the innovation that I will talk about, the starting point for it, is a cheap thermal storage, an innovative solar receiver, and a robust and very simple concept behind it. The potential is, it can be a game changer for CSP. It can be a multi-billion euro and dollar business, and our CSP industry can get into a huge rise. How shall we do this? With a very simple concept, the closed air receiver and solid rock storage. Now this is a very simple system diagram, and some others have done similar before, but the new thing is the receiver in there is closed. So it's not open to the environment, it's not a volumetric receiver, it doesn't have any quartz glass in there. The storage is very, very simple. It's just solid storage, and we use air at ambient pressure to heat it up and to unload it. With that hot air at temperature levels at about 600 degrees Celsius or above, we can go to any type of heat consumer, to steam generation or other applications. So now I will focus on the closed solar thermal receiver. What's the basic physics behind it? The basic principle is cold air cools best. So we send the cold air to the tip of a receiver module. There it cools the surface and then it flows backwards along the inner surface of that receiver cap and heats up on its way. Now, what are the features behind it? We do the best cooling of those areas where waste heat cannot be captured. So that's a tip, naturally. Now, on the way, we have large internal surfaces through cooling pins, which allow us to transport the absorbed heat from the surface into the air and capture it. We need for that heat exchange material that can withstand very high temperatures and has a very good heat conductivity. That's silicon carbide. It's a relatively cheap material which can be used for 3D printing. Now, also, if we add multiple receiver modules of that type next to each other, then we get the cavity effect, because the heat that comes from the surface of the one receiver module hits the surface of the next one, so we are still able to capture some of that heat and bring it into the working fluid. Last but not least is the surface shape reduces the convective heat losses. A flat surface is good for convection, but our surface is not good for that. So, which is good for the efficiency of the receiver. Now, how is the numerical performance? How is the efficiency of such design? Would that be feasible? Can we do this? So we set up a numerical model at an early stage, already 2-3 years ago, and tried to set up the pins on the inner side of such receiver cap. And just with intuitive improvements, we reached a thermal efficiency of 90.7%. And if we include the fan power for the operation, then we reached a receiver efficiency of almost 75%. This was not enough for us, so we applied artificial intelligence to even improve the design, and through that we slightly improved the thermal efficiency to 91%, and we increased the efficiency, including the fan power, to 78.9%, which is in a reasonable order of magnitude. Now, can this be manufactured? And we tried this, and here is first a 3D CAD model, CAD model, with such receiver cap with a diameter of 23 centimeters and a length of 32. And the photo that you see here is now from the inside of such cap, printed with silicon carbide with thousands of cooling pins inside. So manufacturing of this is possible. Next is, well, the silicon carbide used for 3D printing is gray, but we need black surfaces for solar applications. So what we did is we coated a receiver cap with a Pyromark 2500 coating, an old one which is known to the solar thermal power generation. That is good paint. We applied it and it works. We improved the absorptions from 0.856, which is a low number, to 0.969, which is a very good number for solar thermal applications. Now, what about the pressure drop? If we design such device and let the air pass through, how good is the accuracy of our numerics? And we see here on the left the numerical model, or a reduced version of that, and on the right we see a receiver module that we used for testing. Now the blue points and the blue line, these are the results from the CFD calculations, and the orange points, these are the results from our measurement. And this indicates that our numerical model is extremely accurate and that we get very close to the reality with our simulations. The next is, can we reach the temperatures that we predict? And the answer is yes, we can. So here you see our receiver module at the test stand in Mülheim. It's a test stand for ceramic heat shields of gas turbines at Siemens Energy. And we used the test stand for the solar application. The air inlet temperature was 26 degrees, and we were able to heat the air up in that small module to 620 degrees Celsius. And the tip at the outside of the receiver reached a temperature of almost 1000 degrees Celsius. So we could show it is possible to heat air in such a small device. However, we were not able yet to measure the thermal power of the radiators, so we cannot yet calculate the thermal efficiency from the measurement, but that is coming soon. The black coating survived well. It looked as fresh as before after the heat testing, so we are confident that it will durate and hold longer also for further applications. Now, what about making this larger, going from one module to, say, 2 megawatt size? How would it look like? And the answer is it looks good. We just place those receiver modules next to each other and on top of each other, and they form then a circular segment. And here in this case with 51 modules in 12 rows above each other and an angle of 37 degrees, we build that receiver and we see that the airflow velocities and the temperatures remain in a reasonable order of magnitudes. What we apply here is 800 kilowatt solar irradiation per square meter, which is a very high number. It's used for molten salt receivers, and we could go even higher, but that's what we did by now. And here in our model, we raised the temperature from 200 to 700 degrees C with a 90% thermal efficiency and 40 kilowatt per small module. Now, 2 megawatt isn't much for solar applications, so what if we make it even larger? We see here now the results for a study on a solar thermal receiver with closed air, and it has 150 megawatt thermal and still looks good with 3,800 receiver modules and a fully circular design. we reach that required size. And again, the flow velocities and the temperatures look good. So this opens the door for industrial mass fabrication, because all these receiver modules, they all look identical and they can be prefabricated in the factory and only assembled in larger modules on site. Now the entire dimensions of such 150 megawatt receiver look like a diameter of 8 meters, a height of 10 meters, and the pathway, the circular ring for the hot air at the outlet has a width of 1.1 meter. This is, compared to molten salt receivers, not big. It's the same order of magnitude, but we can say our weight of our receiver will be much less than what the molten salt receivers have. So the tower will be cheaper and the foundation will be cheaper. So what did we accomplish through this? Quite a bit, I would say. We have unique features here of this innovation. We have a closed circuit for air as heat transfer fluid. We have low pressure loss for the heat transfer fluid and a minimum loss of heat to the environment. So we reached the 90% thermal efficiency in calculation, and I'm confident we will reach it also in practice. The resistance to temperature is above 1000 degrees Celsius, so we don't have to worry about hotspot from the solar field. The receiver will survive that. No usage of transparent objects, no quartz glass, nothing where dirt can disturb us and where the quartz glass would even overheat from dirt, and solar radiation on top. The receiver is insensitive to pollution from the environment. It's robust and scalable, designed for thermal power from below 1 megawatt thermal to above 100 megawatts thermal, all with the same design. And this opens the door to enormous cost reduction potential through industrial fabrication and mass production of identical receiver modules. What are the next steps in this journey? We will be testing at Sunlight, that's the artificial sun of the DLR in Germany, in Jülich, with 7 modules and 280 kilowatt thermal power. It's already in preparation, and we try to do this very fast. Next step would be possible to do the testing at the solar tower facility in Jülich, Germany, with up to 1 megawatt thermal power. However, the financing for this is not yet secured. And not so much time in the future, we want to go for a pilot project, a commercial pilot project. It should be a small one, and we want to include the thermal storage into this design. And if you should be interested to participate in the pilot project, let me know and we can try to make it happen. Now I suppose you will have lots of questions. Don't worry, contact me. Send me your questions and I will answer in writing, and I look forward to see you next time in Albuquerque. Thank you very much.